Okay, welcome back. In this next video here, we have another example where we're checking to see when is this thing continuous. This time we have a piecewise function that's made up of three pieces. 2x plus 1 when x is less than 2, x plus 3 when x is between 2 and 4, including both 2 and 4, and x squared minus 8 when x is greater than 4. So our task is to look at when is this continuous. Well, if we look first at the three individual pieces, those are all polynomials which are defined everywhere. And so therefore, in the individual names, individual intervals, when we're below 2, it's going to be fine because 2x plus 1 is always defined. When we're between 2 and 4, x plus 3 is defined everywhere. It's going to be fine. And x squared minus 8, when x is bigger than 4, again, it's going to be defined, it's going to have a limit, it's going to be continuous everywhere in the interval. The question here is, what about when it switches? What about when it switches? And so we do have to do a little bit more investigating. We need to make sure when it switches that there's no jump in the graph. If you remember looking back at some of the other graphs that I've given you previously, there's some examples of piecewise functions where you have a jump in the graph, and that's something we do have to avoid. That is something we do have to avoid. Okay, so what we need to look at is as x is approaching 2, what's happening on the left, what's happening on the right? In other words, what's happening with my two pieces? What's happening with my two pieces? So 2x plus 1, if we plug in x equals 2, 2x plus 1 would be going towards 5. 2x plus 1 would be going towards 5. What about x plus 3? Well, if we check as x goes to 2, x plus 3 is going to 5. So both left and right here on this piecewise function are approaching the same number. And so, therefore, at x equals 2, the function is continuous. It's changing equations, but it's still connected. And then we check, what about x approaching 4? Well, the first piece there is x plus 3. X plus 3 is going towards 7 when x is going towards 4. Right, so that piece is approaching 7. The other piece, x squared minus 8, if we plug 4 into it, that would be 4 squared is 16 minus 8. It's going to 8. So the left and right don't agree. They're close. So you might think, can we split the difference and say it's 7.5? No, because we got to be able, for a limit, we have to be able to get as close as possible. And if we did 7.5, then the closest we could ever get would be within a half unit, because it never gets there. And so, therefore, there is a gap in the graph at x equals 4. And so when we talk about our continuity, it is continuous at x equals 2, and it's continuous inside all three of those intervals, but it is not continuous at x equals 4. There's a gap in the graph. So here I wrote this down as x can't be equal to 4. If we did it in interval notation, it would be the interval from negative infinity up to 4, union with the interval from 4 all the way to infinity. Okay, and so that's the question of when is something continuous. In the last video for this section, we're going to look at the types of discontinuities that we can have and talk about that. So stay tuned.